Thank you. So we will start this Ignite talk show now. And now it's going to be on a rail, because even from now on, all the slides, they will be advancing every 15 seconds. So we have 5 excellent speakers lining up, so I think we can start applauding. And in 45 seconds, we have... Yeah, you can come up, Henrik. You know me, come up. So in 45 seconds or a bit less, Henrik's slideshow will start. And perhaps in 30 seconds, it will start. So we can really get a sense of both how incredibly long 15 seconds can be and how incredibly short 15 seconds can be. So without a lot of ado, I guess this is where we just like pedal a tiny bit. From Lunar Way, Henrik Høegh. And
yes, thank you. My name is Henrik Høegh. I have a middle name, but I don't have time to say that here. I work as a platform engineer at Lunar. We are a bank and a tech company and a lot of stuff. I work in something called Squad NASA. I did, but I'll get back to that. I'll talk about promise theory. Here, Mark Burgess, he says promise theory describes interactions between autonomous agents within a system. It provides a semi-formal language for modeling intent and its outcome, which result in chemistry for cooperative behavior. So we're going to talk about obligations and promises. Obligations is basically like top-down micromanagement. Promises in teams is more about autonomous teams that decide how to solve their things. So what do we mean about this? We want to control uncertainty, right? So imagine baking a cake, and this is how much I know about cake. This is an ice cake. It'll be fun later. But following a recipe doesn't always give the right results, right? So why is that? Someone gives you a recipe, tells you by obligation you need to follow this recipe. You need to use this room. You need to do it in exactly this way. And for some reason, it doesn't always work. Why is that? Well, uncertainty, and this is why obligations doesn't work. This is what my cake looks like when I follow a recipe, and my teacher in Folkeskolen can vouch for that. And in this talk, I'm going to talk about why this is, and how we can actually control uncertainty with promise theory. Now, this is how much I know about ice cakes. Some people use a professional oven, and some might use a cheap oven. There's a difference, and we see that in contests on TV. It's not behaving like my oven. There's a lot of uncertainty with tooling. This is a guy from Nailed It, if you've seen that show, not a professional. This is what Google Images portray as a professional baker. Something about skill sets, wanting to learn, needing to learn, knowing what to learn and when to learn it, if you're not in control of that. Humidity, temperature, the same. If you're in a tent, it's not the same as in your home kitchen. If you're not in control of these things, it's a lot of uncertainty that will actually make the cake I just showed you earlier, right? So you can have conflicts. 2 people saying you need to do this recipe, right? And there's a conflict between these 2. The only person that cannot resolve this conflict is the person doing it, if you do obligations. This is where promise theory turns it around. If you go to a bakery, you basically do a couple of promises. The baker promised to give you a nice Danish, and you promised to receive it. You promised to give him money, and he promised to receive it as well. You don't decide how that cake is made. That person knows best. In promise theory, we have simple agents, senders and receivers. It could be atoms, it could be people, it could be software, it could be a lot of things. You give a promise, you accept a promise, it cancels out to 0, and that's the way you know that it's a stable system. This is a kind of weaker system. It doesn't add to 0. The sender wouldn't know where in the chain the error would occur, right? So this is a weaker system. So you can assess a system with a promise theory in this way. This is another pattern where you have a leader or a broker, depending on people or software, whatever you do. And the 2 receivers actually don't know if they agree, but the leader does, in this case, right? So trying to minimize the overhead of having this. We can then group agents in super agents. So in people, it would be something like software. Teams, in software, it'll be something like bounded context. We make promises on the outside and hide the internals. We don't get to decide that. We were in Squad NASA. We split up into 2 teams. How we did that was that the team mapped our capabilities. So what is it we do here? That's a movie reference. And then we actually mapped what's it made of, the dependencies, the capabilities, and of course the promises. And we grouped them. So what's it made of, that's some Git repositories, and so on. And if you listen carefully, if we zoom in, could we zoom in, please? Thank you. We have the promises on the outside, right? What is it we promise? Well, we promise to accelerate developer lead time, customer support, and so on. That's our outside promises. How we solve it is up to us. Nobody gets to decide that. Not even our managers or head of tech or anyone. They don't have technical decision power. We do. Stay out of it, right? And why is that? Well, that's because our team knows best what uncertainty to handle, when to handle it, and how to handle it, to meet our outside promises. So that's promise there for you. I hope you liked the talk, because that was it.
Big round of applause for Henrik. I swear he sent me PDFs and yet he could Zoom. I don't know. That's very magical. So this is where we do the technical switching, and you can also join me. Next up we have Ewelina, who is from Mærkelig, which rings funny in Danish ears, but I think that's on purpose, those crazy Norwegians. So we will be talking about compliance and
don't take away my slides, right?
Sorry. Ewelina!
Yes, thank you. So my name is Ewelina. I am from Mærkelig. And I am here to talk about compliance and what it means in the context of software development. And also I am on the verge of a heart attack right now. Now let's nail down the language. What's compliance? According to the Cambridge Dictionary, compliance is an act of obeying a request, a rule, or an order. But yeah, what does it mean for software developers, and who's making these rules? Many of us are working in some so-called regulated industry, like banks, automotive, medical equipment, and that means we are controlled by government rules. And these are the rules that we have to comply with. Traditionally, compliance isn't something that I would think fits under the DevOps umbrella. We manage to optimize builds and tests, but compliance is still done pretty much old school. So in 2010, the product I was working on was a gigantic application, and it took hours to build. So you build, around noon, you discover there was a typo, you fix it, you run the next build, and you can go home. Can you imagine that now? The servers we were using, the machines we were deploying to, were pretty big, very expensive machines. They were basically impossible to scale, and the teams had to compete for access to deploy or to test. So things were taking a lot of time. We had like 2 releases per year, and delivery stopped for weeks where developers had nothing to do, but the QA team was chasing deadline. Then we had a change management process and a manual deployment. It's a little bit better now. The software we're producing is divided into smaller, more independent units, so we can build and test much faster. Also, a lot has changed in terms of infrastructure. So the machines are cheaper, there is more of them, and thankfully the cloud was introduced, so we can basically spin up the environment we need at any point if everything is set up properly within minutes. So we managed to speed things up. We automated tests, we automated builds, we automated deployments. These things are happening much faster. We can release faster, except the regulated industry, where the change management part is still taking a lot of time. So change advisory board has to meet, assess, prioritize, verify which things we want to release and schedule their releases. And they also have to manually often maintain the information about the compliance. So there's this claim circulating around the internet that after moving to their own cloud, Amazon engineers can deploy every 11.7 seconds. So imagine being the change advisory board that has to deal with all of these changes. And if you read Accelerate, you know that there is a data that tells us that sometimes those external approvals, but by managers, by CAB meeting, are so much hassle that it's better to just skip it. Not everyone has the luxury to do that. So how should it be? From developers' perspective, loosely coupled, rapidly updated software, and many small servers and functions that make the infrastructure basically disappear behind the code. So the productivity charts can skyrocket. They can produce a lot of changes in a very short time. Yet, we still have the change advisory board, actual people that have to do everything manually, and they might not be exactly happy about it. Is there hope? Well, 15 years ago, I wouldn't believe the way we're producing software now would be possible. Even 7 years ago, I was still pretty skeptical. And here we are. We're improving constantly, so I think, well, of course there is a hope. And I think the solution for the change management part is actually pretty simple. We just have to automate it. We've done it before with builds. We've done it before with deployments and tests. We just have to do exactly the same thing with compliance. So we have to start gathering compliance information when we're building, when we're testing, when we're deploying. It's that simple. It solved it. Not really, of course. It requires a little bit of work. And what's the most important part is that DevOps engineers and software developers have to understand what the information change advisory board needs and why they need this information. And then they can work together and make sure that they can automate most of those things. Of course, there has to be still a place for humans in the loop. But once we have it covered, continuous magic can take care of all the boring and repetitive stuff, and we can actually focus on making a change.
Thank you so much. Thank you, Ewelina. So for the next transition, about 45 seconds. Mads, you're welcome to. The slides are working. I think everything is good. Do you have a favorite?
30 seconds to do something.
I'm just trying to stall for time. I don't know if you've noticed. 30 seconds is a long time. So you're from Reload. I guess you will also tell a bit about yourself, yes?
Yeah. Yes. And we're hiring.
And they're hiring. So come talk to Mads. Mads from Reload.
Thank you. So the first slide, I thought that I would have to pedal and wait and wait. So I think I'll start around now. So my talk is about handling complexity and how it's actually quite hard to handle complexity. And it's very important to understand what complex systems actually are. So a complex system is a system that consists of a number of components, n components, and there's a dependency between these components, and they affect each other, and they rely on this connection between the individual parts. Now, if we make a very small change to n, this system gets very, very complicated and very, very hard to predict. We can't really predict in particular how this system is going to act. We know this concept from weather, for instance. We know that it's quite impossible for me to tell you exactly when it's going to rain, even though I can tell you that it's probably going to rain today. Also, we know this from our area, because of course, any IT system is complex because it consists of a lot of parts, and we have a need of all these parts working. You know that some of this is going to break, but you don't know which part. It might be the thing in the bottom, but it might be something in the top. Now, the funny thing is that when it comes to planning, for some reason, it suddenly becomes possible, for some people at least, to predict exactly when something's going to be done, at what cost, and how much is going to be completed, which is kind of weird. Now, the reason we can do this is obviously because we are experts, and we've gotten into this habit of trusting this magic capability of an expert to predict exactly how these complex things are going to work. Now, when I say expert, I think it's important to actually think a little bit about what an expert actually is. So there are many different attributes of an expert, and there are two different types of experts that I'm going to highlight today. So, first off, you have the type of an expert that is very, very good at his or her craft. This is a person who knows how to handle sharp tools and can deliver high-quality results given an input. This type of expert is quite different from the other type of expert, who is a veteran. So this is an expert that has seen some things that you wouldn't believe. This is a guy or a girl who has been through a lot of things and lived to tell the story. This is the type of expert that knows that you probably shouldn't walk into this field, and when someone says, well, you can just integrate these two systems, that person is going to at least triple all his or her estimates. The problem with this type of veteran is that this type of expert can't still predict a complex system in detail because it's still impossible. And it's very dangerous to start relying on this person being able to do this impossible feat. Because in the end, while it is funny to tell war stories, and I mean, we can have a beer over it, it's not funny to go through the actual experience of being woken up in the middle of the night and having to fix production. So we really shouldn't rely on this type of person being able to do something that is, frankly speaking, impossible. Now, the problem is that we are writing more and more software. So if we kept to a small set of software, it might be possible to predict things for an expert, but things are growing. And now the field looks like something like this. So while your expert might have been able to navigate that first step through the process, now you have to traverse this entire field without hitting a single mine, and that's just, frankly, impossible, and we shouldn't rely on this. So what do we do? Well, one option would be to just write less software. Then the problem would go away, right? And I think the horse has left the barn here. It's not possible to actually start writing less software. But what we should realize is that it's actually not hard to work with complex systems. We're used to this. We're used to handle the weather. We should just start stopping making precise predictions and start just looking out the window instead and see whether or not the weather is great. We should also start focusing on the quality of our experts and be okay with not being a veteran, but just being really good at what we do, and start training the next generation of experts to be good at their field. And we should also realize that, a lot of us are experts, and we have experienced this pressure of having to be able to do these impossible things, and we should start resisting that pressure and start being more honest and be more realistic about what's possible. Because in the end, it should be possible for an expert to sit down in the room and say, well, I'm an expert, and I don't know the future, but together I'm pretty sure that we can make our way into a much greater future by taking small steps.
Thank you so much, Mads. And now comes the awkward time again, where we have to pass the time. John, feel free to join me up here.
Hi. It's already me. My talk is going to be about feedback, and a lot of people know I probably do something in DevOps. Some might know, before I did something, I was organizing hardcore events, and those are one of my favorite artists. They're called Drox and Neophyte. They're from Holland. And I was watching a podcast of them, how they explained during COVID they had a problem because they were not going to parties anymore and could not test their tracks on a party. Because they told the ultimate feedback for them is interacting with the crowd, interacting with their fans. And this one is true for DevOps and, of course, for agile software development as well. Interacting with the customer and actively listening what they're going to tell you, what they want, what their needs are. And this is the best type of feedback you can get. And here, actually, they're interacting really with the crowd. During COVID, they tried other stuff, like performing streams out of a prison, but that was not the same than standing in front of people, talking to them, and actually see their reactions and interact with them. So, here you see him much more happy. And after that, they explained their production process in kind of talk. And they were explaining, well, they go to rave, and after that, they're going back to their studio and get their impressions and their Ds, and they explained kind of cycle, and studio, rave, reactions, ideate. Even their cycle got faster by having new technologies. Like in the old days, they played vinyl records and pressed them before going on party, and now they have a digital. And this one reminded me on the Deming circle. It's actually the same. It's plan, do, check, act. Well, what you know from Deming, and actually Deming is one of the root things of DevOps. Well, the plan phase, you need to consider which points to get feedback on, how you actually will measure later if you get success with what you're doing or not. The next one is do, and actually do, you have to keep the flow. When you do stuff, in psychology, flow is different than in lean. You should not get disturbed and out of it because you work perfectly in the way you are doing at the moment. And that's what you need to consider. Don't disturb the feedback, the flow part. Well, you need to check your feedback. And I know two types of feedback basically broken down. We got human feedback, which I get from other people using your system. And we got technical feedback. Well, technical feedback cannot replace everything. You can train along the feedback you receive. And here I have a good example for that. It's the little patience game, and there's always a noise when you touch the line. It's a good thing to train by feedback. Doing experiments is kind of natural. When I started programming, I was trying it in very little steps. Maybe somebody is knowing Gorillas, which was in QBasic. And actually, I did some kind of TDD cycle. You always need to consider this. There also can be misleading feedback. Back in 2004, I developed an app called Moblock with my company. I went to a club taking pictures, and people just told me, well, nobody wants to stand on a party and take pictures from a mobile phone. Well, 10 years later, I was the only one dancing. Oh, well, but our product did not had success. But sometimes you need to make your thing. Sometimes you will receive negative feedback, but you need to continue anyway if you believe in it. Well, you can even provocate negative feedback, like Neophyte. He has a song, "No one likes us, but we don't care." Well, no one will like the Chaos Monkey if you're going to introduce it. In DevOps, we got different sources from feedback. Well, we got it from your team, interact with them. We got feedback from testing, but, well, the best feedback is still from production, and see how people interact with your system. And things crash on production, which could not be tested before. Well, if you ask me for the top three metrics, a lot of people do it. It's incidents, it's releases, and the time you're waiting for others. And best way, do direct interaction. Well, which feedback loops should you have? You have certain feedback loops in Scrum, and Scrum says your feedback loops can be as long as you can risk to do something wrong. That's the length of your feedback loop, and now I ask you for some feedback, and maybe you can give the next speaker a bit feedback. Maybe you can clap your hands every second, and we can try it until the next slide starting. Can you? Yeah, that's good.
Thank you so much, John.
Thank you.
A big round of applause. And I think we now see one of the implementation details, because it has neither been 30 seconds since John was speaking, nor is it 30 seconds until you. So let's see what happens next. This looks more like it. You better join me up here. One never knows what will happen. So next up we have Christian. He is the last of our courageous Ignite speakers, I'd say. And if I know Christian right, we will get to end this little session on a tad more technical note. Is that yes? And you have sound and everything?
Yeah, I have sound.
So I'm not sure that we should give him like the 15 seconds of full applause. That might just go to his head. But I think from Epicode Technical Agile Coach, Christian Clausen.
Thank you. I'll just wait for a second for it to start and breathe before. Yeah, hi. Let's talk about principles for functional programming. My name is Christian. I'm a technical agile coach. The important word there being technical, because what I do is more similar to that of a software architect than most agile coaches. And I work for Epicode. I also talk fast. In this talk, we're going to use an object-oriented language, sort of like Java, but without all of the access modifiers, because I needed to save space on the slide. We're also going to look at a simple stack implementation. That's because it shows three of the most common problems that we experience with object-oriented code. The first of them being null pointer errors. Here, they are in peek and pop. We can have null pointer errors because we use a null to represent an empty stack. So that can give errors there. Another source of errors commonly in object-oriented code is side effects, and there are three areas that are interesting here for that. There are the two assignments, obviously, but we also have this helper class that's entirely mutable, meaning anyone can do anything to it at any time. So that makes multi-threading really hard to reason about, and it also means that if two different parts of the system have a reference to the same stack, one place can change what the other one sees. That can be very difficult. Due to the way that we use generics in this example, we also cannot implement a general map function, and by map I mean something that takes a transformation and applies it to every element in the stack, like adding 2 to every element. If we try to do that, we get something like this, where we actually have the input and the output type having to be the same because we have this assignment to the head, and we're reusing the same components. So that's not the map function that we actually like. We can do int to int, but we can't do int to object. The first principle we're going to talk about is immutability, and you will see I highlight important things with purple, so just look for those mostly. So immutability, we can get that here by just adding final to all of the fields in the program so that we can't assign to them anymore. That also means that before, where we had void functions, it doesn't really make sense to have void functions because they associate with side effects, and we can't have that anymore. So instead, we wrap them, all of the return values, in a new stack. So we all the time generate new things. If we look back at map now, actually, we have a problem because before, we were assigning to head, which is now illegal because it's final now. So instead, the solution is to apply principle number 2, use recursion. So we have this map helper that actually goes through and replaces all of the nodes with new nodes instead of reusing the old nodes. That also has the added benefit that we can now have a different output type for whatever the map thing is. So we can now have T to B. The reason we have to use recursion is because the data type was recursive. Recursive data, recursive function. So that sort of goes together very nicely. The next thing, if we go back and look at the stack, we'll see that we have this stack is actually just a wrapper for some immutable data now because top is just immutable. We might as well just delete the field and then expose the node directly. That's not dangerous because it's immutable, so there's no danger there. And that's what we've done. That also means actually that we can take the T that was before on the class level and push it down to the method level. And that is principle number 3, prefer later binding. Now each of these could even be static, and this is not so much a stack as it is just a bunch of utilities for a stack. So we do the renaming as well. Principle number 4 is not to use null. And in this case, we use null to actually represent an empty stack, and that doesn't work. So instead, we employ something called the null object pattern, where we actually have a new type of class called empty that is supposed to replace our nulls, and then an interface, of course, so that we can they both inherit from that. That also means that we can now specify if we want something that's possibly null, i.e. the stack, or something that's definitely not null, like the node down here. So we can no longer have null pointer exceptions, because these are always defined if we have a node, which is really nice. Yeah, we have a problem back in map because we are using this equals null check, and we don't use null anymore to do anything. And Java programmers will immediately say, what about instance of? But principle number 5 says we're not supposed to rely on runtime types, so no casts and no instance of. So that doesn't work. The solution is to use what's called algebraic data types, and it sounds really fancy, but it's actually just visitor pattern. So we introduce a new function called map that takes an object of the type with that has one method for each of the data types that we have, so empty to empty and node to node with the appropriate data passed as an argument. And if we smack that back into our map function, we'll see that we have the if null becomes just an empty over here and the else becomes a node over here. Everything else is the same. Well, almost. If we go back and look very carefully over here, we'll see that this ST down there, that one actually points to the original one, meaning that this over here was an infinite recursion. In fact, all of the map functions we've seen on the slides have had infinite loops in them, which is another common error in object-oriented programming, whereas this one does not, because the inner one shades the outer one, so that one actually works. If we compare it to an actual functional programming language, we'll see that not only does it have the same structure, it has literally the same syntax, just with a bunch of boilerplate because Java. That's actually everything I wanted to talk to you about. I've written a book about refactoring object-oriented code, and you can find me on the internet. Thank you very much for listening.